So here's the squeeze theorem in a nutshell. They give you a few examples in the section, but here's the idea. If I had a function that was forever in between two other functions over its whole domain, right? So what does that mean? What's one way you could represent that visually? So we can have, if this is my g of x, let's say g, so g of x has got to be the smallest one. They could all be equal to each other, just be a line. Ooh, that's exciting. Right, that was one extreme. But yeah, I have my g function is doing its thing. Woo-ha! And I have my h function doing its thing. How many colors do I have? So h has got to be, at most, it's got to be equal to that or something. So here's the idea. Here's a. Here's my h function coming in. Let's say that right there, the limits are the same. Right there at a. So this is my g function. It's the lowest one, right? G of x is smaller, and sometimes it could be equal, right? H of x is the big one. It's the biggest one out of all of them. Sometimes it might be equal. F has got to be where? Say again?
In between.
Yeah, F has got to be, it could be, it can do whatever the hell it wants to in there, right? It's got to be in between. It could hit one or the other one anytime it wants to, because it could be equal to one of them anytime it wants to or needs to, or it happens to be. The whole point here is, what's the limit of F as x approaches a? So if I know the limit as x approaches a of g of x is L, and I know the limit as x approaches a of h of x is L. So all I know is this and these two things. This is why I love it. It's called the squeeze theorem. Bless you. Normally, the simpler the name, the harder the theorem. I don't know, when you get further in math, you'll start to see what I mean. But this simple name actually goes with a very simple idea. That limit has to be what for f? Yeah, you can see why they call it the squeeze theorem now, right? There's no other options for it. If this goes to L and that goes to L and F is always between these two, it's also got to go to L. There's no other way. So how do you use that? I don't know. Okay. So if I wanted to know what's the limit as x goes to... Oh, take one. Yeah, they got some weird ones in here. Doesn't really matter. Yeah, okay. As x goes to 0, bless you, of that. I like it. You'll start to see what kind of functions we can use. Sine is an interesting function because I'm always guaranteed that the output of sine must be between what and what?
1 and -1.
I don't care how weird the inside looks. The output can only go between -1 and 1, right? Is that cool? That's why sine is such a beautiful function most of the time. This one's got a weird-ass inside, but I don't care. The outputs have to be between 1 and -1. Right? So that's how this comes into play. Sine of 1 over x can be at most what and at least what? I just said. And you just said -1 and 1. Is that cool? So I'm building my g and my h function based on the boundaries, the bounding of part of this. Is that the function that I want to say something about? No. So how do I get the rest of it in there? I just multiply everything by x squared. And then I get negative x squared is less than or equal to x squared sine 1 over x. Less than or equal to x squared. That's true, right? And now take the limit as x goes to 0 of these two outside ones, and it will force the middle one to do something. So what's the limit as x goes to 0 of this? 0. And what's the limit as x goes to 0? Get out of there. Of this? 0. So therefore the limit as x goes to 0 of this must, now you can say it's 0. Right? So people make the mistake of plugging a 0 in there, but then you plug a 0 in there and you can't. It's a special form of indeterminate. It's forever oscillating. So you can't say this is the official way to prove it. So what other kind of function? Obviously, I could also put cosine. What else?
Tangent.
Not tangent, but
Cotangent.
inverse tangent. Oh, shit. What is it about tangent? Can you draw a tangent very quickly for me? What is it about tangent? Is tangent continuous from infinity, negative infinity to infinity? No. Ruh-roh. What's tangent look like? It looks cubish. Do you understand what I mean when I say cubish?
Yes.
But it's got asymptotes where? Ruh-roh. Because what's tangent of pi over 2? Tangent is sine over cosine. What's cosine of pi over 2? Cosine likes x, and I'm on at pi over 2, I'm on the y-axis, is 0. Shit! So that's why there's asymptotes there, right? So there's asymptote here, asymptote there, and then it's cubish, and then it repeats. So the inverse would just be that flipped, right? Therefore, inverse tangent is bounded by negative pi over 2 and pi over 2. So you could also have an inverse tangent there, and then it would be, instead of 1 and negative 1, it'd be negative pi over 2 and pi over 2. You could do the same thing with inverse tangent, but there's only certain functions that would really work nicely with this. You can use a modified squeeze theorem for other functions, but we won't apply modified squeeze. Okay? Maybe? Is that? So squeeze theorem is really kind of nice. It's, on one level, it's almost too easy to believe. But on another level, it's important that you build correctly. Start with just the part that you know is bounded, and then multiply in all the rest of the shit, right? Okay? Anything else from homework? Is homework going okay? Yes.
Number 62.
You're my go-to man back there. And in which same section?
Yeah.
Oh, yeah. This one, I love this one. So, before I do 62, recall, if I had the limit as x goes to 3 of, I don't know, what you want to say, Jeff? You can do it! Yeah, okay. Good. Trying to make one that works. So if I plug a 3 in, what do I get? Yeah, I get 0 over 0, right? Is that cool? You can't stop there, right? I've graded a few homeworks where people just say that equals 0, which is neat. You can never divide by 0 and just say it's 0. You have to do some work to prove that, and maybe it isn't. So this means, when I get this, that means my work has just begun, right? If I get 1 over 0, that means my work is done. Then it's infinity. And I'm done. Yay! But if I get indeterminate form, my work is just started. And what do? We've done something like this before already. I like it. So this problem, I'm not going to do it. You multiply by what? Rad x minus 2 plus 1. Right? That's the conjugate. And then blah, blah, blah. And somewhere the x minus 3 is going to cancel eventually, right? It's got to. The whole point of that is to kill the problem. And you're guaranteed the problem will be killed. Right? So the actual question here is limit as x goes to, what was it? 2. Square root of 6 minus x minus 2 over square root of 3 minus x minus 1. I love this problem. So how many pieces that look like this are there? There's 2. So how many times do you think I'm going to have to do something like this? Twice. Yeah. That's a neat. I love that problem. You got to conjugate this bad boy, and you got to conjugate that bad boy. Each of those gets its own step. The person that did this, you can't multiply this by its conjugate and this by its conjugate. That's illegal because you've multiplied top and bottom by different things, right? You can't just say, well, I need to. I don't give a shit. Math won't let you do it. So you have to do the conjugate bam bam and the conjugate bam bam. I love this problem. Yes?
So you start from the top?
It doesn't matter. Take care of them. It doesn't matter what order you do it, right? Sounds like a mob. Just remove the prop. Sorry, this is why I'm a math teacher, not a mob boss. This is one reason. The other, I tried it, didn't really work too well. Is that cool? That's a good question because it's weird. But it's just like when you have two radicals in an equation, you're going to have to square twice eventually, right? So you got two radical crap in the ratio. You're going to have to apply two conjugates to kill them. Okay. Anything else from homework?
Yeah, I have Webassign, so it looks something like this, but it's number 5.
Which section?
2.4. Small screen.
Oh, this is the graphic calculator?
Yeah.
Sure. Let's illustrate the definition.
It's number 5.
Oh, okay.
Number 5.
Largest possible noise. Okay, cool. So real quick, let's because we didn't, I love Thursdays. They're done by the time we get started. Let's do one example, because we did one on the calculator with epsilon delta stuff that was a straight line. So if it's curvy, I mentioned that it won't be symmetric. So remember when we had 3, and we found 2.875 and 3.125, delta was 0.125. If you weren't here yesterday, you have no idea, but it was perfectly symmetric because it's a straight line. If it's curved, it won't be symmetric. This won't be in the middle, it'll be far and then close. So let's talk about how do you figure out what delta is then if you have two options. So real quickly then. Oh, we're gonna log in. And tomorrow I'm reteaching the tutors about epsilon delta in case they had one of the scared teachers that didn't want to do it. I'm sorry, I shouldn't say that about my colleagues. They disagree with me that it's something we should do. So it's like any field, there'll be disagreement, and they have the right to be wrong. It's okay.
Come on, section 2.4.
Yeah, section 2.4.
Oh, wow.
You don't believe in that?
Yeah, I was like, it's like a discussion thing. That's up for discussion. Like, which ones you guys should cover?
Oh, totally. Yeah. We have meetings about like 160. Some people use calculator. Have anybody taken stats? So I have students come to my class that failed another class. And they say, "Oh, my teacher last semester let us just push buttons and get the end." I'm like, "Well, you didn't learn shit." So we have a big discussion in the math department. What's the maximum level and the minimum level of calculator usage we would allow in 160? So there is flexibility and there are differences of opinion, and we're all mathematicians, so we respect each other. Although I keep talking like I don't respect them. I don't want you to. I gotta be careful. I respect their opinion, but it's an opinion. Yeah, it's true. All right, sorry. So, what was the function that was on that one? We might as well do your problem for you because you're actually asking me. Oh, I'm sorry, buddy. I'll make up another one. Don't worry.
Okay.
Um,
I have it here though. It's x cubed negative.
All right, guys. Let's put this in here. So x cubed. If you want to play along, if you just want to sit there, you can.
Negative 5x plus 7.
And what's the limit as x going to what?
2.
2. All right.
And then equals 5.
I'm sorry. What? Oh, yeah. So the limit is 5.
Yeah.
Okay. All right.
No, the limit's 2, but the whole equation equals 5. So
The limit as x goes to 2, right?
yeah.
And this is something from Webassign of this function, right?
Yeah.
And that limit is
5.
5. Cool.
Yeah.
All right. So that's the statement, and of course you just plug a 2 and you see it's 5, right? So on one level, I don't blame you guys. And is it? Let's check them. We plug a 2 and I get 8 minus 10 is negative 2 plus 7 is 5. Cool. So right there, I'm sure a lot of you guys are like, so yeah, Jeff, your colleagues are right. I got the answer. Why do I have to prove shit? I understand that reasoning, but this is building a foundation for, building on top of that later. So visually, if I graph this function, and I'm curious about, so hit zoom 6 so we're all on the same page at first if you're playing along. So that's what it looks like. I'm curious around the point 2, right? And what else did it say? It gave us an epsilon, right? Did you already put it away again?
Sorry.
That's all right. I keep not asking you everything.
Epsilon 0.2.
Okay. So epsilon is 0.2. So I don't know, who remembers the first thing we had to do? What's that epsilon talking about? Which axis is epsilon talking about? The y-axis. So what do I want to build epsilon around then? The supposed output, or the outputs approach this, right? Is my claim. So around 5, I want to build my little neighborhood. So how far up am I going to go?
0.2.
Yeah, so it'll end up at 5.2.
4.8.
And 4.8. So that's my region around that limit, around that number that's supposed to be my limit. And now I'm curious if 2 really does cause this function to approach 5 as I approach the input of 2. If it does make it go to 5, then I should be able to find a neighborhood around here that makes the outputs stay within that area, right? That's the idea. So what I do is, I've already got the function plotted. If I put in here also the restrictions this way, it's got to go up to 5.2 and down to 4.8. And of course, it's probably going to have the same thing seen. So now we want to zoom in. And I'm curious about the 0.2, so I want to zoom in around this point right here. 2, 5. So I'm going to zoom box. You can zoom in too. I don't know what it's going to do for you, but I like zoom box. Control it more. So just like that. Bam. Now it should open up nice for me. So there's the upper. There's the lower. Cool. I think about this right. Yes, cool. It's not as curvy as I hoped it was. It's just a little bit of a curve to it, so it shouldn't be too crazy. So then how do I identify, just like in the book, they also draw the delta on the x-axis has its own kind of like little lines, and then makes a little box up here. How do I find where those are? I just have to find what? Intersection. So starting at this input, whatever it is, and in the middle of this is 2, right? So starting on this side up to this side, those outputs always stay within that far. So some dude, some jerk says, all right, it's got to be within 0.2. And then I go, okay, I have to find a range on my x-axis that always has outputs that close to the supposed limit. That's the whole idea, right? And if it really is the limit, I should always be able to do that, no matter how small they make epsilon. The minute I can't do it, I don't have the right limit. So then just find the intersection. So let's see. And again, this is a little bit curvy, so it's not going to be symmetric around 2. So to find this intersection, second calc. No, Jeff. Second calc. Intersect. Let's find this intersection. Enter. 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 So I get 2.0279. Oh shit. Well, you guys know how to do that. So over here I get 2.0279. Is that cool? So it looks like maybe delta is going to be 0.0279, right? Well, let's get the other intersection. Second calc. Intersect. Down here. Enter. 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 1.97. Let's see. 1.9707. So this is so a delta candidate here would be 0.0279. What's the delta candidate here? Is everybody cool with that? Where did I get that from? That's what? How far away? That's what delta is, right? It's the distance away from the x value, limit value, right? So what's the delta candidate from this guy? 2 minus this is what? 0.0293. Are they the same?
No.
So which one do you think you pick?
Less than
Exactly, because if I pick this, then I would go that far out in both directions. And how far am I allowed to go out in this direction? Only that much. So it only makes sense I'm going to pick the smaller one to be my official delta. That's the first little weirdness that you introduce when you have a nonlinear function, right? You're not going to have a symmetric region around your x value.
You always pick the smaller one?
Say again?
You always pick the smaller one?
Totally, yes. Because that's the distance away that you're allowing. So this is the most I can go up, this is the most I can go down. To guarantee that they end up, I have to take the smaller one. Because if I go too far, it's going to be outside of where I'm supposed to be. So then I pick the smaller. So your proof would be like, let delta equal the minimum of blah, blah, blah. You can imagine. That's what I meant by I make the function just a little bit harder, and the proof becomes possibly quite a bit harder. Is that cool? Is that all right? Or is that tolerable? All right. Or somebody out there, I'm just not going to do 2-4. Let's see what he does. And somebody's like, yeah, I was thinking exactly that. Okay. Okay. So anything else real quick? It's already 1 o'clock. I love it. All right. So what I want to focus on today, 2.7 and 2.8 are fundamentally the same thing. Let me just show you the difference and then formalize what I want you guys to do. Let me see if you can put together some stuff that we've already done. That sounds scary. So if I want to know, we want to know the slope of f of x equals x squared minus 2 at x equal to 3. Yeah, some of you guys are showing up. It's 6. So yeah, it's 6. If you know derivatives, you know how to do that. Real quick. We don't know derivatives yet. Too bad. Aw. Alright, so the function... some of you guys did section 2.1 incorrectly. You didn't find slopes. You just plugged x's in and got y's out and said that's the answer. The whole point of that section is finding the slope. So that was the first step you did. So if you plug a 3 in and you get 7, ooh. It's not what it's asking. It wants to know what's the slope of this function at that point. Right? So how do I do that? We know how to do that. We have a couple ways to do it.
Plug in 3 first to get the output, and then, I don't know.
The actual output of the function at the point doesn't matter at all. Really. It will, but in general it actually doesn't. It doesn't have to have a value. It just has a limit.
Is it the f of x plus h minus the f of x?
Yes, so one way to do it is, what's the slope of anything? It's y2 minus y1 over x2 minus x1, right? I like it. So it, oops, sorry. So if I want to know the slope at 3, and I got my my parabola there, and I want to know the slope, I can say, okay, I can go to 3 plus h. And then I can how do I make that get closer? Why is that not close? Because of stupid plus h. So how do I make it get closer? I let h go to 0. Wouldn't that bring it in closer, right? So if I let h start at 1, and then I make h 0.5, and then make h 0.1, that's basically what that first section was doing to you when they said finish this table. 1.5, 1.1, 1.01. You're getting closer to 1 in that case, right? So I want to let, as h goes to 0, in general it's this. In general it would be a plus h minus f of a over a plus h minus a, which is just h, right? So when you see this, you forget that this is just the slope. But the bottom had stuff cancel. It is y2 minus y1 over x2 minus x1. That's all this is. Maybe. So if I want to know the slope of some function at a, I take a point that's h away. So this would be f of a, and this would be f of a plus h. So then I do y2 minus y1 over x2 minus x1 to get the slope. And calculus says, no, I want to know what the slope is at one point. And we go, Okay, calculus. You're weird. But we'll take the limit because we eternally need 2 points. We eternally need 2 points. So that's what will make it always 2 points, but it will tell me what it looks like if it's approaching if it was 1 point. Does that make sense? That's the underpinning of calculus right there. Right at the beginning of it. All right, so what the hell is the practical application in this then? Well, what is A in this case? What is A? What point am I interested in? 3. So A is 3. So that we just got to figure out. Now I do have to figure out what f of 3 is, right? There are other ways around it. It's freaky, but this direct way, I need to figure out what f of 3 plus h is. I need to figure out what f of 3 is, and then I can plug them in, right? We did stuff like this. Absent the meaning of what this is, we did stuff like this before with limits. But now we know what the meaning of this is. Right? There's a whole homework problem. There was 2a plus h minus 2 was the answer, whatever. You had to go through all this crap and the h is canceled. If you let h go to 0, you actually get the slope function. So what's f of 3? Let's start there. We got her 7. What's f of 3 plus h? Help me, God. Don't. I appreciate you speaking up, but no. Right, you got to plug 3 plus h in and then do it. Are you guys with me? I mean, f of 3 plus h is you plug a 3 plus h in place of x. You don't just tack it at plus h on the end. We know better than that. So what do you get here? You get 9 minus 2 is 7. I like it. Plus 6h plus h squared. I like it. All right, let me stop there for a second. Foil it out, right? You gotta foil this bad boy out. 9 minus 2 is 7. H3 is 6h, and then h squared. When you foil it, you should all be able to do that. So if I do this, I'll get the limit as h goes to 0 of that minus this, which was the number of points is 7. Just want to make sure you guys are out there. All over h, and of course, what happens?
7s go, and then
Yeah, all the non-h stuff goes away. Please tell me you brought water. Good. So the 7 goes away, and then I can cancel an h out of both of those, right? Is that cool? So what do I end up with? I end up with limit as h goes to 0 of 6 plus h. 6, right? So anybody who's never had calculus before, sitting around the dude that said 6 earlier, you'll see why. There's shortcuts to this. All right. So help me out. What is that? The slope. Yeah, good. So at 3, this tangent line would have a slope of 6. So let me go one step further. Can you find the equation of the tangent line at that point? You can't. Okay, good. It's sort of like a game show. You find that equation in 3 data points. In 2 data. I could name that tune in 1. No? That was really old show. That's before my time. Name that tune. I'll stop. So to find the equation of the tangent line, at what point? What point is it? 3, comma?
6.
What's 6 again? What's 6?
6 is the slope.
6 is the slope. What's the point? 3, 7. Now it's easy. Now it's algebra. How did we get the slope? Who gives a shit? We got it. So in algebra, how can you get the slope? Like I say, it's perpendicular to this line. Remember that? And you had to find the slope of that line. You have to negative reciprocate it. Who cares how you got the slope? You do the same damn thing. In fact, I always call it the SDT level. Once you get the slope at a point, you do the same damn thing. Right? You plug it into y minus y1 equals mx, or you plug it into mx plus b and get the b. Who cares? Whatever you want to do, you do the same thing. Right? So y equals mx plus b. 7 equals 6 times 3 plus b. So b is... Does this sound familiar? I'm doing this a little quickly because this is a freaking algebra. Yeah, so 18, so minus 11. So y, the tangent line's equation would be y equals 6x minus 11. Now, since I got this guy up here, this is kind of cool. If you put in here the original function and the tangent line, it should look, it's going to look better, but it should look like this, shouldn't it? That's the whole idea. That's kind of cool. It's a visual verification of the work you've done. So if you put in here x squared minus 2, and you put in here, what did we just say? 6x minus 11. My scale is all freaky. I'm not going to be able to see far enough up. Alright, so if I look up just a little bit, now already it looks good, doesn't it? But if I change my scale a little bit, let's make this negative 5 up to, what was it? Okay, yeah, up to 8's fine. And then let's make this negative 4 up to 16 maybe. There, it hits right there. It hits at that one spot. It hits right at 3. Bam. Is that cool? That's exactly what a tangent line is supposed to do. Those of you playing at home, there you go. So it's nice. It's nice to be able to verify what you've done. So if I ask you to find the equation of a tangent line to a function, you can plot the function and plot your answer. And if your line goes like that, I think you're wrong. Right? It should look like they should hit that at that one point and then keep going. Yes, sir.
So we got negative